Hi everyone, my name is Pranay Manocha. I'll be presenting our work, which is titled Contrastive Learning for Perceptual Audio Similarity. This is joint work with me and my advisor Adam Finkelstein and folks from Adobe Research, Zheyu Jin and Richard Zank. So let's get started with the presentation. Let's do a listening test together. Consider this reference audio clip.
Obscurely in the recesses of the house after the fact.
Now which sounds more similar to it, audio 1
Obscurely in the recesses of the house after the fact.
or audio 2?
Obscurely in the recesses of the house after the fact.
So you probably all thought audio 1, and indeed humans we tested also agreed. However, conventional metrics like L1, L2, PESC, and VISCOL actually chose audio 2. We see that these metrics don't correlate well with human perceptual judgment. So our goal in this project is to build a perceptual metric that reliably agrees more often with humans. The task of audio similarity is to compare different audio signals, and it is an extremely important task for two reasons. One, researchers rely on these similarity metrics to evaluate and compare algorithms, and it's often used to guide the improvement of these algorithms. And two, these similarity metrics, if differentiable, can be directly optimized for as a loss function in deep learning, which is extremely important for designing good algorithms. As we saw, conventional metrics like L1, L2 are just numerical differences that cannot reflect human perception of similarity. Early perceptual models like PESC and VISCOL were inspired by the way human ear processes these signals, but these approaches are not robust for audio samples that are quite close and have subtle differences, like in the example that we just heard, and two, they're non-differentiable. Differentiability is crucial in many deep learning and other tasks that require a gradient for optimization. To address the non-differentiability aspect, researchers looked at differentiable PESC, like the two works here. These metrics were approximations of PESC and so are not robust to unseen audio and unseen audio perturbations. Researchers have also explored GANs as a similarity metric, like the work of metric GAN. These approaches are too task-specific and may not be easily optimizable always. Finally, deep feature losses from a pre-trained network have been used and explored extensively, as in the case of style transfer by the work of Katis et al. However, since we are using repurposed weights from a different task, those might not generalize well across all tasks. Our paper last year introduced a new metric called DPAM, in which we directly trained a model on a large dataset of collected human judgments. The resulting metric DPAM correlates well with MOS ratings across 4 different tasks and can also be directly optimized for as a loss function in speech enhancement. Let's look at it in some more detail. To collect human perceptual dataset, we focused on just noticeable differences, or JND, asking a simple, unambiguous question: are these recordings exactly same or different? This allowed us to study human perception near JND, which is extremely important in various audio tasks, especially in cases where we would like to enhance the audio quality as perceived by a human. To sample a large variety of population levels, we crowdsourced it using Amazon Mechanical Turk to be able to collect a dataset of around 80,000 paired human judgments. We also used an active learning sampling strategy to efficiently sample from this huge space. After collecting the dataset, we train a model on these judgments. By directly learning a perceptual metric from data, we produce a metric that correlates well with MOS tests than traditional metrics such as PESC. Furthermore, we show that the metric can be directly optimized for as a loss function for the task of speech enhancement. However, the DPAM model also has a few shortcomings. The DPAM model suffers from a natural tension between the cost of data acquisition and generalization beyond that data. It requires a large set of human judgments to span the space of perturbations in which it can robustly compare the audio recordings. Moreover, the metric may generalize poorly to unseen speakers or content, since speech also impacts the acoustic embedding. Finally, because all the data is focused near JNDs, it is less likely to be robust to large audio differences. To ameliorate these drawbacks, we introduced CDPAM, a contrastive learning-based multidimensional deep perceptual audio metric. We use contrastive learning here as a pre-training self-supervised strategy that augments a limited set of human annotations with unlimited data. To reduce the dependency of acoustics on content, we use a multidimensional representation learning strategy to separately model content similarity, which is the similarity amongst different speakers or utterances, and acoustic similarity, which is the similarity amongst different recording environments. This multidimensional or disentangled representation also reduces the number of samples that are required to learn an embedding. And finally, to further improve robustness to large perturbations, which are well beyond JNDs, we collect a dataset of judgments based on triplet comparisons. This combination allows CDPAM to better generalize across content differences, for example, unseen speakers, with limited human annotations. Talking more about the newly collected triplet comparison dataset, it consists of triplet comparison questions, asking a bunch of human listeners a simple question: is A or B closer to reference C? The dataset consists of around 30,000 paired judgments, and it enhances CDPAM's ability to robustly compare files with large differences. Now, looking at the model architecture, we first pre-trained the encoder using contrastive learning, and then fine-tuned the encoder and trained the loss network using the perceptual dataset that we collected in our previous work, which was DPAM. And finally, we fine-tuned the whole model using the newly collected triplet comparison dataset. Let's now look at each and every step individually. So the basic idea in contrastive learning is to augment the audio in various ways, and then to maximize the similarity between the representations for the same audio in contrast to the representations from an unrelated piece of audio. Let's look at it in some more detail. So we take a bunch of clean audio recordings and then apply a data augmentation module to add two kinds of perturbations. One, adding noise to existing clean recordings, and two, to sample another audio recording of the same quality. This step is somewhat different from the conventional contrastive learning approach. So let me explain further. On the left, you see a common Sinclair contrastive learning framework where you have an image of a cat. You then apply the augmentation module, which performs transformations like crop, resize, blur to the original image. The final goal is to learn an augmentation invariant embedding of a cat by forcing the embedding of the transformed images close together for each original example. However, in our case, as we are doing multidimensional learning by learning acoustic and content embedding separately, we assume that every audio recording can be broken down into its acoustic component, for example, amongst the different recording environments, and the content component, that is between the different utterances. So to learn the acoustic embedding, we apply augmentation that keeps the same perturbation and levels, but changes the content of the recording. We thereby force the model to learn the content invariant acoustic information. On the other hand, to learn the content representation, we apply augmentation that keeps the same content but changes the perturbation level and type, thereby forcing the model to learn the acoustic invariant representation. We then embed the transformed audio waveforms using the audio encoder and then get the respective content and acoustic representations. And finally, we transform the high dimensional encoded representations to a lower dimension for contrastive loss. The contrastive loss maximizes the similarity between representations from the same clean recording while minimizing the similarity between augmentations from two different recordings. The second step is to train a loss network on the JND dataset that we collected in our previous work and which I also briefly explained before. This calibrates the metric on JND-like small differences. And finally, we fine-tune the metric on the newly collected triplet comparison dataset to make the metric robust to large beyond JND type perturbations. This makes CDPAM robust to large order perturbations. To measure the performance of this metric, we first check for correlations with MOS. In this work, we extend the datasets that we look at to include various diverse publicly available datasets like audio source separation, the voice conversion challenge, and also the conventional noisiest dataset, which is a non-deep learning based speech enhancement dataset with MOS ratings. Overall, we look at 9 different datasets and check how well CDPAM correlates with the MOS ratings. I won't go into details on each dataset, but the takeaway point here is that CDPAM is able to correlate well with MOS ratings across various datasets as well as various triplet 2AFC tests. In an ablation study, we found that the contrastive learning approach is able to disentangle content and acoustic dimensions pretty well, as well as it behaves as a very good pre-training strategy for learning a rough quality measurement. Just a simple contrastive learning model trained without any perceptual calibration also has a non-trivial positive correlation with MOS ratings across datasets, and this correlation further improves as we train on more perceptual data. To further see if CDPAM can improve upon the existing state-of-the-art real-time speech denoiser, we supplement our model CDPAM in two different ways. First, we train the model using a combined loss including CDPAM from scratch, and second, we pre-train the model using conventional losses and then only fine-tune using CDPAM. Now, looking at the subjective MOS ratings, both our models are able to achieve higher scores than the baseline. Let's listen to one such example. Let's take a listen to the noisy recording first.
You were described as being in a serious but stable condition yesterday.
Let's now listen to the baseline demux performance.
You were described as being in a serious but stable condition yesterday.
And finally, let's listen to our model's performance.
You were described as being in a serious but stable condition yesterday.
Specifically, we observe that CDPAM can identify and eliminate minor human perceptible artifacts that are not captured by traditional losses. Next, we also show the utility of a train metric as a loss function for the task of waveform generation. We use the current state-of-the-art Melgan vocoder and train two different models. One, a single speaker model trained on a single speaker LG dataset, and second, a cross-speaker model which is trained on a subset of the VCTK dataset. We take the existing model and just add CDPAM as an additional loss in the training objective and observe that a subjective pairwise comparison prefers our model always better than the baseline. Let's listen to one such example. For the cross-speaker synthesis case, let's first listen to the clean audio recording first.
Rarely put nose out of doors or sit.
Let's now listen to the baseline Melgan performance.
Rarely put nose out of doors or sit.
And finally, let's listen to our model's output.
Rarely put nose out of doors or sit.
Specifically, we observe that Melgan enhanced with CDPAM detects and follows the reference pitch better than the baseline. So in summary, we designed a self-supervised multidimensional audio similarity metric that correlates well with human subjective MOS ratings across tasks, as well as works as an optimization objective in deep learning for waveform comparison tasks like denoising and synthesis, and can also detect and reduce perceptible artifacts that cannot be reduced by conventional losses. So this finally brings me to the end of my presentation. Thank you all for listening.